Look at this satellite feed of the North Atlantic. From the ground, a sudden downpour or a clearing sky feels entirely unpredictable, but that local chaos is an illusion. What you experience as daily weather is the strict mechanical output of a highly organized planetary-scale machine. Solar energy fuels this engine, creating an extreme thermal imbalance. The equator absorbs massive radiation, while the poles suffer a severe heat deficit. To fix this, the atmosphere acts as a global heat engine, transporting excess equatorial heat to the freezing north and south. Every cloud, gust of wind, and raindrop across the mid-latitudes is a byproduct of that transfer. To understand why it rains where you live, we must look at how this planetary engine moves air and how we measure it. The Earth doesn't push warm air north in a simple straight line. The planet's rotation and surface dynamics organize this heat transfer into massive, looping convection currents. We can map the outer boundaries of this system. Intense heat rising at the equator forms the Hadley cell, dominating the tropics up to 30 degrees latitude. At the other extreme, cold, dense air sinking at the poles drives the polar cell, covering the high latitudes down to 60 degrees. Trapped between these two is the Ferrel cell, spanning from 30 to 60 degrees latitude. This middle zone is the geographic home of Western Europe and countries like Ireland. The critical feature here is the exact latitude of 60 degrees north. This is the polar front. It is a highly volatile atmospheric boundary where warm air moving up from the tropics is forced to collide with freezing, dense air pushing down from the Arctic. That collision doesn't gently mix. The conflicting air masses fracture and twist, generating the vast, rotating frontal weather systems that dictate the mid-latitude climate. Driving this entire boundary zone, roughly 10 kilometers up in the troposphere, is a high-speed wind current known as the polar front jet stream. This high-altitude river of air acts as a rapid steering mechanism. It grips the low-pressure storms generated at the polar front and pulls them east, directly across the Atlantic Ocean toward the European coastline. While the jet stream pushes storms horizontally, the precipitation inside those storms relies entirely on vertical movement. To analyze this, we define atmospheric pressure strictly as the physical weight of air pressing down on the Earth's surface. In a low-pressure system, or depression, warm air is less dense than its surroundings, so it rises. This vertical lift triggers the specific thermodynamic process required to generate all rainfall, adiabatic cooling. As that parcel of air gains altitude, the weight of the atmosphere above it decreases. This drop in surrounding pressure forces the rising air mass to physically expand. Expanding requires energy, and as the air expends that energy, its internal temperature rapidly falls. The air continues to cool until it hits a strict thermal limit known as the dew point. At this temperature, the air can no longer hold water as a gas. The moisture condenses into liquid droplets, forming heavy clouds and ultimately rain. We contrast this mechanism directly with a high-pressure system, or anticyclone. Here, cold, dense air is heavy enough to sink toward the surface. As the air descends, the increasing atmospheric weight compresses it. This compression causes the air parcel to warm up. Because warmer air can hold more moisture, condensation becomes physically impossible, ensuring clear skies and stable conditions. Rain is never a random event. It is the strict physical output of adiabatic expansion. Without that initial vertical lift and subsequent pressure drop, precipitation simply cannot exist. For adiabatic cooling to trigger, the atmosphere requires a mechanism to force the air upward in the first place. While weather fronts and thermal convection from hot ground provide this lift, massive topographical features act as permanent engines of uplift. Look at the west coast of Ireland. The rugged mountains of ranges like the 12 Bens stand directly in the path of incoming Atlantic weather. This topography creates relief or orographic rainfall. When prevailing winds push saturated maritime air inland, it immediately hits a physical wall. The mountains act as a massive ramp. The saturated air is forced upward along the terrain, violently triggering adiabatic expansion. It cools, hits the dew point, and drops intense precipitation almost entirely on the windward western slopes. By the time this air mass crests the peaks and continues eastward, it has dumped the majority of its moisture. As it slides down the leeward side toward the flat midlands, the reverse thermodynamic effect takes over. The air descends, compresses, and rapidly warms, shutting down any further cloud formation. This mechanical rain shadow is why the western seaboard is defined by boglands and heavy rainfall, while the eastern coast maintains a significantly drier climate and entirely different agricultural soils. To translate these physical mechanisms into actionable forecasts, meteorologists continuously measure shifts in atmospheric pressure and temperature at ground level. The raw data collection begins with physical surface instruments. Equipment like the Stevenson screen is designed to ventilate thermometers while shielding them from direct solar radiation, securing an accurate baseline reading of the true air temperature. Alongside temperature, capturing the physical weight of the atmosphere is critical. Instruments like the aneroid barometer track the minute rise and fall of pressure, detecting approaching systems long before a cloud appears. Today, millions of data points from stations across the globe are fed into supercomputers to generate a unified, real-time spatial map. The result is the Synoptic weather chart. This map is the geographer's code, allowing observers to visualize the invisible thermodynamics occurring miles above our heads. The structure of this map is defined by isobars, continuous lines connecting areas that share the exact same atmospheric pressure. There is a core rule to reading this data. When you see isobars packed tightly together, it indicates a steep pressure gradient. The atmosphere is rushing to balance itself, which translates directly to severe wind speeds at the surface. The charts also map the exact collision zones between contrasting air masses, marking them with specific boundary lines known as fronts. A warm front, marked by lines with half circles, indicates warm air slowly sliding up and over a colder air mass. This gradual climb triggers slow, steady adiabatic cooling, resulting in persistent, long-lasting rain. In contrast, a cold front is marked by lines with triangles. Here, dense polar air bulldozes underneath a warmer air mass. This forces the warm air into a rapid, violent vertical ascent, generating heavy downpours and thunderstorms. These abstract two-dimensional map symbols are exact translations of three-dimensional thermodynamic realities. Decoding them allows society to accurately predict and prepare for extreme conditions. We can now zoom back out to the planetary scale and observe the high-altitude engine steering these systems, the jet stream. The chain of causality is unbroken. The global thermal imbalance drives the jet stream. The jet stream steers the local pressure systems, and those pressure systems force the adiabatic uplift that dictates our weather. But this entire mechanical sequence relies on a stable baseline, and global climate change is rapidly warming the Earth's poles. By heating the poles at an accelerated rate, the energy gradient between the equator and the Arctic diminishes. Without that severe temperature contrast to drive it, the jet stream loses its momentum. It slows down and begins to meander in deep, unpredictable wobbles. The physical consequence is severe. A weakened jet stream fails to push storms quickly across the ocean. Instead, massive weather systems become trapped inside these deep bends, stalling over specific regions for weeks at a time. When a low-pressure depression stalls over Western Ireland, the topography forces relentless adiabatic uplift day after day, saturating the ground and causing catastrophic local flooding. The inverse is exactly the same. A trapped high-pressure anticyclone locks sinking, compressing air over a region, shutting off precipitation and triggering prolonged agricultural droughts. Weather is a precise, interconnected machine driven by the transfer of heat. By decoding its mechanics, we realize that altering the global temperature physically rewires the engine that sustains our local environments.